Howdy. I had a few questions about counting parameters with the design matrix. So I'm just going to do a quick review and then show you an analytic method that you can use for most simple models that we use, and then go over some examples. So as we talked about last week, there's two reasons why a parameter might be non-identifiable. One is due to intrinsic non-identifiability, when you have, for instance, the final P and phi in the Cormack-Jolly-Sieber model being confounded due to model structure. And secondly, extrinsic non-identifiability, where a parameter that's in a model simply can't be estimated by Mark because the data are inadequate, the parameter is close to 0 or 1, or maybe both things are going on, and it's simply unable to come up with an estimate based on the numerical methods that Mark uses. In terms of estimating the number of parameters, a true number of identifiable parameters in a model, you can use an analytic approach where you calculate based on intrinsic non-identifiability. And we went over some of the simple models last week and how you can do that. But it gets more complex as things get more complex, models get more complex. So I'm going to show you a more general analytic approach you can use. But as we talked about last week, Mark actually counts the number of parameters that are estimable using a numeric approach. Um, Again, the Mark book goes into a lot of detail about this in terms of the two approaches that are used, threshold versus ratio methods for the um, Hessian matrices. And one thing that Mark does do when the two approaches that it uses, the two numeric approaches, don't agree, it gives you a call out, that says check parameter count, because the two methods that it's using aren't agreeing with one another. But that I found sometimes it'll give you that when the count is actually correct, and other times it'll give that to you when it's incorrect. Um, and so Mark can either overcount or undercount the number of parameters in a model. And obviously that has some real consequences for identifying the potentially the top models in the model set. And as we also pointed out last week, the approach that Mark uses, or the link function that Mark uses when you're using the parameter index matrix versus the design matrix, can cause the number of parameters that it estimates in a model to differ. With the parameter index matrix, the default link is still the logit link, but you can use a sign link because you have a identity matrix when Mark is running the parameter estimation, and the sign link works with the identity matrix. And the sign link is better at estimating parameters near boundaries. So, when there's an option of running a model either using the PIM or the design matrix, you're probably better off using the design or the PIM and setting it to the sign link to just see if there's any problems, and we'll show an example of that. With the design matrix, you can only use the logit link, and as a result, it's more likely to undercount the number of parameters in the model when you are using the design matrix. Again, just going over the approaches to counting number of parameters. You can write out the saturated capture history as discussed in the Mark book. One thing I didn't mention last week, and again, this just gets into a lot of the weeds, but there's an approach that can be used called data cloning, where basically you take the same capture history information that you have, but you just increase the sample size associated with each one of those capture histories. The default is to increase it by 100, but you can increase it by 10,000 or a million or however many you want to, and then run the model again to see if those parameters are now estimated correctly. But that still has some issues with it, and again, there's a lot of detail on this in Appendix F that can help you out with that, but I really think we're getting too far into the weeds for this course. But if you have some complex models that you're having trouble with parameter estimates, it might be something to consider. What I'm going to show you on the next slide is a analytic approach that can be used for correctly calculating the true number of estimable parameters for most of the Cormack-Jolly-Sieber models that we'll be encountering. And then I just wanted to add one additional point for those of you who might be considering using RMark. RMark is a version of Mark that can run using R programming, and basically it calls program Mark, has it run all of the analyses, and then brings all the data back into R and allows you to do some other things, including plots and that sort of thing that might be helpful, but I'm not going to go into that. It would just be too much, and frankly, I'm not very familiar with running models in RMark. But one thing to be aware of is that RMark just defaults to using the total number of parameters in the model, not necessarily the number of estimable parameters. So it doesn't take into account the non-identifiability. And as a result, it's going to overestimate the number of parameters in the model. And basically, Jeff Lake, the person who wrote RMark, felt like it's better to overestimate the number of parameters because that will reduce the risk of choosing an over-parameterized model. So if you can imagine a big model that has like 48 parameters that are potentially estimable, and Mark can only estimate 20 of them because your data is really sparse and there's lots of your P's and P's are coming out to be 0 or 1. Then that model is probably going to pop right up to the top because it's going to say, gosh, we're able to get a pretty low log likelihood, and we don't have that many parameters. So, gosh, this is a really great model, when in fact it's maybe one of the worst models. So he errs on the side of caution of avoiding those highly over-parameterized models. So here's a nice table that just provides all of the analytic approaches to estimating the number of parameters in the Cormack-Jolly-Sieber model for a lot of the models that we'll be covering. So group times time, group plus time, time, group. Big T is something we haven't quite referred to yet, and that's a situation where you have a linear time effect, where you're trying to see if there's a straight linear change in either phi over time. It can be positive or negative. Is phi dropping linearly over time, increasing linear over time in your data? Same thing for P, which could be, obviously a model of real interest if you're looking at a threatened species for instance, and you want to know, over the 20 years that you've been studying the species, is there evidence that survival has been declining? But anyway, you can see that this just gets really ugly really fast because there's all these different equations for calculating the number of parameters that are estimable. So for the GT, the phi G times T, P G times T, for instance, it's G times, in parentheses, 2 times T minus 3. If you put G plus T in for the P, now it's G times T plus T minus 3. So, it's kind of uh, overwhelming, obviously not something you're going to be able to memorize. Some of this is intuitive when you think about how these parameters might be confounded in the final time step, for instance, and we talked a bit about that last week, but this is a way to just kind of check everything. This last one here in the lower right corner is just 2, where you have phi dot p dot, okay? Um, and what I've done is I've put this into a spreadsheet. So all you need to do is enter the number of groups, the number of sampling occasions, and if you're looking at a linear time effect, then the number of parameters is just determined by the fact that that linear time effect is in the model. So you don't need to do anything special for that. And these are all the equations for calculating that. So I've stuck this into a spreadsheet where you input G and T and boom, it'll output all the estimates for all of the models. Now I have just uh, developed this table. I think I've gotten all the equations right, so I'll give you anybody who finds one that's wrong and using this, I'll give you 5 points extra credit. And hopefully everything's right, but it would be helpful if you guys took a close look at it and checked it. So that Excel spreadsheet I'll put up on in this module. So here's I'll use the Swift data now because there's some issues with um, Mark and how it counts parameters. If we start with the most general model, remember the Swift data, there's 2 groups. These were the good colony and the poor colony, and 8 occasions, okay? So when we set up our PIM chart, we have a total of 14 parameters that can be estimated for phi, a total of 14 parameters that could potentially be estimated for p, okay? Um, but the final phi and p are confounded for both of those groups, right? Because you're estimating phi and p separately for each group. And so those final ones for male or for the good colony and the poor colony are going to be confounded. So, if you think about it intuitively, it would be 28 minus 2. But, using the equation that I just provided you, both of those approaches would give you 26. And Mark correctly estimates the number of parameters in this case. So moving to a additive model now, again, this is one that could only be run on using the design matrix because we can't do additive models on the PIM. Now there's a potential for 8 values to be parameters to be estimated for phi, 8 for p. You put those 2 together, that gives you 16, but the last time interval, phi and p are confounded, but you only have 1 pair of parameters that are confounded rather than 2 as in the last model. And so you'll only decrease your parameter estimate by 1 in this case. And you see that if we use that standard equation that I just gave you, that also gives you an estimate of 15 parameters, but Mark actually estimates 16, okay? So in this case, it overestimates the number of parameters. So you'll have to adjust that number of parameters down by 1 to get the correct AIC value for the model. So now let's look at model phi g p g times t, and we got a couple of interesting things that happen here. First of all, note that the total number of parameters is just 2 for phi, because we got phi g, and then 14 for p. So that gives you a total of 16. And of course, there's no problem with non-identifiability in this model, or intrinsic non-identifiability, because there's no t associated with phi. So the correct number should be 16. Okay, but if you run mark using the design matrix for this model, which of course you don't have to, um, because it could be run with the PIM. But if you do it with a design matrix, because it's using the logit link, it'll only estimate 14 for the total number of parameters in the model, okay? And so as a result of that, that model pops up very close to the top of the model list. However, if you either adjust the number of parameters using adjust parameters in mark, to the correct number, which is 16. Notice how that really drops that that model in the list. Has very, very low AIC weight in that case. And so, this is a case where if mark is estimating things incorrectly, it can really bump that model up and make it seem like it's a great model when in fact it's not. The other thing that you'll notice, I don't know if you can see here, but if I run this model using the sign link, using the PIM structure, it also correctly estimates the number of parameters. So that just shows you where, when using the sign link, you can sometimes get better estimates of parameter number than with the logit link. Not always going to happen, but it can. And so, it's just important to make sure that the number of parameters is estimated correctly. Uh, so just a quick summary here, just a reminder that the design matrix approach can only use a logit link. It's more likely to underestimate the number of parameters because of difficulties associated with that link. So it's probably always important to calculate the number of estimable parameters using the analytic approach, and check it against what mark produces and adjust the number of parameters if needed.